Okay, let's unpack this. We live in a world utterly transformed by large language models, these incredible systems built on the transformer architecture. They're amazing at understanding and generating text. But there's a fundamental challenge, right?
Mm.
They really struggle to process very long sequences of text efficiently. That core mechanism, self-attention,
Yeah, the self-attention.
its cost grows quadratically with the sequence length. The longer the text, the faster the computation just, well, explodes. It's a serious bottleneck.
That quadratic scaling is absolutely the key hurdle, I think, for pushing into truly long contexts. And that's exactly why a lot of recent research has turned towards alternative architectures, specifically state space models or SSMs.
Right.
You see names like Mamba 2, Longhorn, these offer linear or, near linear complexity relative to sequence length, which is vastly more efficient for long inputs. And they're better on memory during inference too.
Right. So the obvious idea that emerges is, okay, why not try to get the best of both worlds? You want that powerful representation capability that transformers are known for,
The representation power, yeah.
got combined with the SSM's efficiency for long sequences. That's the promise of these hybrid models. But here's where the complexity really kicks in, especially if you're starting, as most people are, with a massive, incredibly complex, pre-trained transformer model.
Yeah, these huge pre-trained beasts.
You have hundreds of layers, and you want to swap some of those expensive attention layers for efficient SSM blocks. Which ones do you pick? It's not immediately obvious, is it?
Exactly. Previous attempts often resorted to pretty simple, sometimes, well, ad hoc methods, like just replacing attention layers at fixed intervals throughout the network, maybe every 5 layers or something.
Kind of arbitrary.
Pretty arbitrary, yeah. But after extensive pre-training on vast amounts of data, these large models develop intricate internal structures. Different layers might learn to do quite different things, potentially leading to, functional specializations or even redundancies across those layers. They aren't just interchangeable building blocks anymore.
And that brings us right to the core subject of our deep dive today. We're looking at a fascinating new framework called RAD, which stands for Redundancy-Aware Distillation.
Rad, yeah.
We've been digging into some really insightful sources for this, excerpts from the original academic papers, some briefing documents, and a study guide. Really interesting stuff.
And our mission in this deep dive is to really understand this novel ARD framework. It offers a much more principled and data-driven way to build those hybrid models by tackling that exact challenge. How to intelligently and effectively choose which transformer layers to replace.
It's about being smart about the replacement.
Exactly. We're going to explore the truly innovative ideas that make this approach stand out academically and why the results they demonstrate, particularly on demanding tasks like reasoning, are so compelling.
Get ready for some genuine aha moments as we guide you through the clever concepts underlying RAD. So let's really get into the weeds on that core problem and the hypothesis driving our RAD. As we've said, the transformer's self-attention has that quadratic cost, making it a computational bottleneck for long sequences.
The big bottleneck.
SSMs, by contrast, efficiently handle long sequences by processing information sequentially and maintaining a compressed state, giving them that linear complexity and memory advantage during inference. This makes building hybrids very appealing.
The appeal is undeniable, combining the representation power of the transformer with the efficiency of SSMs. But the challenge remains. Starting with a pre-trained model means you inherit its learned structure. Simply swapping layers arbitrarily might disrupt that learned function. You might break something important.
And this is where that central hypothesis of RAD comes in. The sources suggest that because of this extensive pre-training, some of those computationally expensive attention layers in a large transformer might actually be redundant relative to their performance contribution.
Redundant, yeah, that's the key word.
They're computationally heavy, but maybe their specific learned function could be replicated more efficiently, or perhaps their contribution to the final output isn't as unique or critical as other layers. Identifying these is the key to optimization, not just replacement.
Precisely. The driving idea is find the layers that are costing a lot computationally, but aren't strictly indispensable for generating the model's output fidelity, and those are your prime candidates for replacement with an efficient SSM block. But how do you figure that out in a principled way?
Right. How do you find them?
This is where RAD's first step introduces a really academically innovative approach. It's quite clever.
Yeah, this first step completely repurposes a technique usually used for speeding up inference. It's called speculative decoding.
Right. Speculative decoding's standard use is inference acceleration. You have a large, complex target model and a smaller, faster draft model.
Okay.
The draft model quickly guesses a sequence of tokens, and the target model then verifies them in parallel. If the target accepts the draft's guess, you can skip running the full target model sequentially for those tokens, achieving speedup.
Okay, I know that technique, but RAD uses self-speculative decoding. The draft model isn't a separate, smaller model. It's actually derived from the target model itself.
Exactly, that's the twist.
And here's the clever part, as you said. They construct this draft by intentionally skipping specific attention layers of the target transformer.
Exactly. So the draft model is like the original transformer, but deliberately handicapped by removing certain attention layers. Then they run this crippled draft model alongside the full target model in a speculative decoding setup.
Okay.
And here's the really interesting hypothesis they test. If skipping a certain set of attention layers in the draft leads to a significant increase in inference throughput, meaning the combination of the draft and target generates tokens much faster.
While still maintaining a reasonably high token acceptance rate by the full target model. So the guesses are still mostly good.
Yes, that's the connection. A high acceptance rate indicates that the draft model, despite skipping layers, is still proposing tokens that are highly likely to be correct according to the full target model.
Hmm.
So if you can skip layers and get much higher throughput without the target rejecting most tokens, it implies those skip layers were computationally expensive, but not essential for maintaining output fidelity in this specific speculative setup.
Ah, I see. So they're identified as computationally redundant candidates for replacement.
Exactly. It's a brilliant academic pivot, turning an optimization technique into an analysis tool. Really creative.
That's really thinking outside the box. And finding the optimal set of layers to skip to maximize that throughput, that sounds computationally brutal. You can't just try every single combination, right?
Oh, absolutely not. For a model with L layers, the number of possible subsets to skip is 2 to the power of L. For modern LLMs, that's an astronomical number, completely intractable to search exhaustively.
Yeah, forget about it.
So the sources explain that RB uses Bayesian optimization, BO, DIBO, is a sophisticated technique designed for efficiently searching complex, high-dimensional spaces like this, especially when evaluating the objective function, which here is running speculative decoding and measuring throughput is expensive.
So it's a smarter search strategy.
It intelligently probes the space, trying to find the best configuration without needing to check everywhere. Much more feasible.
Okay, so step one is essentially using BO guiding self-speculative decoding, which is intentionally skipping layers to empirically discover which attention layers are most computationally redundant based on maximizing inference throughput while maintaining output fidelity. The sources mentioned they used Llama 3.2-3b instruct as the base model for this diagnostic step.
Right, measuring throughput using greedy self-speculative decoding on sample data. And their ablation studies provide crucial evidence for this. They really back it up.
What did the ablations show?
They show that the layers identified this way, what they call the opt layers, consistently yield significantly higher throughput when skipped compared to arbitrarily chosen layers, or those selected to have low throughput when skipped, which they called worse layers.
Okay.
This strongly validates their novel diagnostic method. It shows it's really finding something meaningful.
All right, so we've used this clever diagnostic to identify the attention layers right for replacement. What comes next in the RV framework? Step two.
That takes us to steps 2 and 3. Constructing the hybrid model and then distilling knowledge into it. In step 2, you take those specific attention layers that were identified as redundant using the diagnostic, and you replace them with your chosen SSM blocks, could be Mamba, Mamba 2, or Longhorn in their experiments.
And this isn't just a simple copy-paste swap. There's a really critical detail about how the new SSM blocks are initialized. Right, this is another academic innovation they highlight.
Absolutely. This initialization strategy is key, and the sources really stress its importance. They copy the outproj weights from the replaced attention block to the new SSM block's outproj. That's, well, somewhat standard practice in some prior work.
Okay, that part makes sense.
But the truly novel part, the academic insight here, is they zero initialize a part of the inproj layer weights of the new SSM block.
Zero out part of the input weights. Why zero? That seems counterintuitive if you wanted to learn something new, right? Why not random initialization?
It's academically elegant because it ties back directly to the diagnostic step. Remember, the layers were identified as redundant because skipping them increased throughput while maintaining fidelity in that speculative setup. Skipping a layer is essentially preventing its computation from significantly impacting the next step.
Okay.
Zeroing out the input projection of the new SSM block is designed to initially mimic that skipped state. It means the SSM block initially contributes very little to the model's output, effectively starting its contribution from near zero.
Ah.
And the sources explicitly state that without this specific zero initialization, training performance degrades dramatically, and the training loss just doesn't decrease effectively. It gets stuck.
Ah, okay. So by zero initializing the input side of the new SSM, you're making it behave initially, like the layer you just determined was redundant when skipped. Like you're starting the training of this new component from a state that's already aligned with the teacher model's output when that layer was effectively bypassed.
Precisely.
The study guide mentioned this helps minimize the initial difference, like the KL divergence, between the teacher and student outputs, making the distillation process start from a much more stable and efficient point.
Exactly. It's a carefully designed initialization that leverages the insight gained from the diagnostic phase. It's not just a random trick, it's principled. And this leads smoothly into step 3, redundancy-aware distillation.
And the redundancy-aware part implies that we're training the hybrid model, learning from the original transformer as the teacher, but in a very specific, focused way. Is that the idea?
Yes. In the self-distillation scenario where you're using the original transformer as the teacher.
The model teaching itself, basically.
Right. The redundancy-aware aspect means they only train the parameters of the newly added SSM blocks. All the original transformer parameters that were not replaced remain frozen.
Ah, okay. So you freeze the old stuff.
You freeze the old stuff. This intelligently focuses the training effort on integrating and optimizing only the new, efficient components that replace the identified redundant layers.
Got it. So the original transformer acts as a guide, but only the new SSM parts in the hybrid are learning and adapting, and the loss function is straightforward.
Yeah, quite straightforward. Just the forward callback libeler or KL divergence between the teachers and the hybrid students' output logics. Essentially, you're just trying to make the hybrid's predictions match the teacher's predictions as closely as possible.
Makes sense. Simple and direct.
Correct. It's a targeted, efficient distillation process, and it's really bootstrapped by that clever zero initialization we talked about. The sources also note that this RE approach works effectively in standard distillation settings too, where you might distill from a larger external teacher and maybe train more parameters then, so it shows some generality.
Right, we've walked through identifying redundancy, building the hybrid with that crucial initialization, and the targeted distillation. But the real proof is in the pudding, right? The performance results. What did they actually achieve?
The empirical results are quite striking, I have to say, particularly concerning reasoning capabilities. They used Llama 3.2-3b Instruct as their base model for the self-distillation experiments.
Okay, how did they perform on general tasks first, like standard benchmarks?
On standard language modeling benchmarks, the RA models showed competitive performance, sometimes even slightly exceeding the original Llama 3.2-3b Instruct teacher model.
Wow, okay.
That's a strong starting point. You've replaced expensive layers with efficient ones without sacrificing and maybe even slightly improving general capability.
But the results on reasoning tasks, like GSM-8K for mathematical problems and CRUX for coding, this is where the paper highlights something really interesting, maybe even surprising.
This is arguably the major result from the self-distillation work. The RAD hybrid models, distilled from the same base Llama 3.2-3b Instruct teacher, significantly outperformed that teacher model on both GSM-8K and CRUX.
Wait a minute, the student model beat the teacher on these specific tasks? How does that happen? That feels genuinely counterintuitive. I thought distillation was about matching the teacher, maybe losing a little performance for efficiency.
It does feel counterintuitive, and the sources discuss this. It's an instance of what's sometimes called the born-again effect in distillation.
Born again. Okay.
Yeah. The hypothesis from the paper is that RAD achieves this by effectively reallocating the model's capacity. By identifying and replacing the computationally redundant potential layers with efficient SSMs, and then focusing the training on those new components, the hybrid model might learn to process information or utilize its parameters in a way that is more effective for these complex, multi-step reasoning tasks compared to the original model's configuration.
So it's not just about compression. It can actually be about functional reorganization and optimization, like finding a better way to use the parameters for certain jobs.
Exactly. That seems to be the idea. It's a potential positive side effect of this targeted replacement and training.
That's a fantastic outcome, showing that this principled approach isn't just about speed or memory, but can actually enhance specific demanding capabilities like reasoning. What about long context tasks? Did replacing attention layers hurt there?
They evaluated on benchmarks like long bench and passkey retrieval. Even though these self-distilled RAD models were trained with a relatively short context window, 2048 tokens, I believe.
Pretty short for long context tests.
Yeah, but they showed resilience on most long bench tasks. The Longhorn-based RAD model in particular performed very well on passage retrieval. The authors hypothesized this might be related to Longhorn's specific design, maybe its online learning properties and its ability to recall past information effectively.
Interesting.
They do note, however, that passage retrieval was one task where the specific choice of replaced layers seemed more sensitive. So not universally robust, perhaps, but still strong results given the short training context.
Okay, so the born-again effect on reasoning and self-distillation is a big headline. What about standard distillation, where you use a larger, more powerful teacher model? Does RAD help there too?
Yes, it does. Here, RAD showed significant benefits in training efficiency and its ability to leverage smaller teachers effectively. During standard distillation, RAD achieved up to about 2 times faster convergence compared to baseline methods.
Twice as fast training. That's a massive gain in terms of computational resources and time for researchers and developers. That's huge.
Absolutely, it's a very practical benefit, and the sources demonstrate through training loss curves that the crucial geo initial. Oh, hey, I think our listeners got something to say. Absolutely, that's a great idea. Let's do a rapid rundown of the main takeaways.
Okay, so picking up from training efficiency, the paper really emphasizes that zero initialization.
Yes, that zero initialization of the SSM input weights is crucial for that faster convergence in standard distillation.
And when they looked at overall accuracy with a teacher model,
Impressively, RAD models distilled from a smaller 8 billion parameter teacher could match or even beat models distilled from a much larger 70 billion parameter teacher on general tasks.
that's a huge difference in scale.
It is, and the advantage was even more pronounced on those reasoning tasks like GSM-8K and CRUX.
So smaller teacher, better results on hard problems.
Exactly, highlighting the efficiency of the RAD approach, and the ablation studies really backed up the importance of their layer selection method.
How so?
They showed that picking layers based on their throughput metric was significantly better than picking arbitrary layers.
Made a real difference in performance.
Absolutely. Now, the authors did discuss some limitations of their work, of course.
Like what?
Bayesian optimization, while effective, might not find the absolute best layer configuration.
Understandable.
And measuring throughput can have some experimental variability. Also, they mainly focused on replacing half the layers in their experiments.
So there's room for future exploration.
Definitely. But the big takeaways about RAD are its novel way of identifying redundant layers using self-speculative decoding.
Turning a speed-up trick into a diagnostic.
Precisely, and the importance of that specific zero initialization for efficient training.
Leading to better performance, especially in reasoning.
Exactly. And the potential to get strong results even with smaller teacher models in standard distillation.
So overall, a really promising and innovative approach to building hybrid models.
Absolutely. It shows a smart way to integrate different architectures.
Well, that gives us a great overview of the rest of the key findings. Thanks for keeping us on track.
Our pleasure. We hope this rapid recap was helpful for you. Thanks for joining us for this deep dive.
And thank you.